if you look at the graph on page 2, I've written a small program in order to describe what this sequence Bn looks like over time. And as you can see, I'm not sure if you can read the numbers unless you look really close, but it drops off incredibly fast, where x is the number of primes less than or equal to n. But luckily, there's something we call the prime counting function that tells us exactly how many primes there are. And the prime counting function, by the prime number theorem, is approximately, I believe, n over ln of n. So just to reiterate the main summary, all we did was, in the beginning, I gave you an intro to showing that rational numbers actually have rational approximations that converge really slowly, and all we did here was transform this into an integral, then transform a rational approximation to another integral, then we bounded the rational approximation and showed that it converged much faster than any rational number.
Good afternoon to everyone. It is a genuine pleasure to welcome you to today's Medgar Evers College colloquium, and we're honored to have with us Suborno Isaac Barry, a remarkable young scholar whose passion for mathematics has already garnered some international recognition, and so at just 12. He's the youngest student at NYU studying mathematics and physics. And this work that he's going to share with us has been done in collaboration with Dr. Wadim Zudilin. And it's about the irrationality of zeta 2 and zeta 3. And, Suborno will say something about the zeta function, but it turns out that if one can say something interesting about the zeta function, you'd be immortalized. So it's one of those areas of mathematics that everyone is secretly working on, trying to figure out the zeros of the zeta function, but they don't ever say it because they don't want anyone to think that they might be wasting their entire lives. So we're hoping that he's not actually working on the zeros of the zeta function, but things peripheral to the zeros of the zeta function that might ultimately lead to some understanding. I should say, this is work that builds on, really legendary mathematicians, Euler, Apéret, and, he's been, mentored by, mathematicians like Barry Mazur, who some of you might know, and Sylvain Capel. So, we think he's on his way to contributing to really deep questions in number theory that we hope will continue to challenge us and inspire us across the mathematical world. So we have this really wonderful opportunity to welcome Suborno to share his insights. And I should say one last sort of personal note. I somehow his name sounded familiar to me, but I wasn't quite sure. And then when we chatted, he noted that he had come to Medgar Evers. There was a guy here who was a former VP named Jerry Postman, and he'd visited with Jerry Postman as a 2-year-old.
It's magnesium! Oh my goodness! You know everything! And this one?
Or a 2.5-year-old. And so the colleagues joined me in welcoming Suborno back to Medgar Evers College. Welcome home.
I'm Suborno Barry. I'm 12 years old, and I'm a bachelor's student in math over at New York University. So today, I'm just going to give a short introduction to the general world of analytic number theory, and in specific, irrationality. So it's a very interesting topic. So the first thing you have to note about irrational numbers are, obviously, they're not rational. So to be formal, an irrational number, or to be more clear, a number alpha is irrational if it cannot be written as the ratio of two co-prime integers P and Q. So that's a pretty simple definition. I mean, that's the simplest definition you can possibly get of irrationality. An irrational number is something that is not rational. So sometimes this definition suffices. Like, for example, if you want to prove that the square root of 2 is irrational, this definition works perfectly well with a proof by contradiction. You assume that it can be written as the ratio of two co-prime integers, then you square both sides, multiply both sides by q squared, and suddenly you have a paradox. Because clearly, this means that p squared is even, because it can be written as 2 times an integer. But if p squared is even, that implies that not only is p even, but p is divisible by 4. So, that means that p is divisible by 2, which implies that p squared is divisible by 4. But if p squared is divisible by 4, that implies that 2q squared divided by 4, which is 1/2 q squared, is an integer, which then implies that q squared is divisible by 2, which then implies that q is divisible by 2. So suddenly, we have a common factor between p and q. But we were supposed to write this as a co-prime ratio. So that means these two can't possibly share a common factor. So p is even and q is even, despite the fact that they're supposed to be relatively prime, which means that p and q cannot exist. So sometimes this definition is perfectly fine, but sometimes with numbers like zeta of 2, this definition doesn't work at all. You can't execute a trick the same way as you can with this. So instead, we'll explore it with a little bit of a different direction. So let's come back to the square root of 2 and start trying to define an irrationality measure. So let's say I want to approximate the square root of 2 the best I can with rational numbers. So let's say I have a sequence AN. So I want to start with a rational number that has 1 on the denominator. Then I want a rational number with 2 on the denominator. Then I want one with 3 on the denominator, and so on and so forth. I want this infinite sequence. So I'm going to lay this out for the first 7, let's say. So we want to put an integer on the numerator of each of these such that it's as close as possible to the square root of 2, which is about 1.41423-ish. So let me check the sequence of integers that I have. So of course, when we're starting with a denominator of 1, we can choose any of the integers, 1, 2, 3, etc. So the closest one is just going to be 1, because there's only a difference of 0.414. So then, when we have a denominator of 2, we can choose something like 3 on the top. This is 1.5, which means the difference is only about 0.09. So the difference has already gone down by a lot. Now, when we have a denominator of 3, we could choose 4 over 3 or 5 over 3. But the closer one is 4 over 3. And we can actually continue this pattern with 6 over 4, which you'll notice is identical to this fraction, 7 over 5, 8 over 6, which you'll notice is identical to this fraction, and 10 over 7, which is the closest you'll get so far, as it's about 1.428. So there's only a 0.014 difference, which is really, really small. So, as you can see, this is rapidly approaching the value of the square root of 2. So, why don't we define a different sequence that just describes the error of the sequence? And in fact, if you look at the graph on page 2, I've written a small program in order to describe what this sequence Bn looks like over time. And as you can see, I'm not sure if you can read the numbers unless you look really close, but it drops off incredibly fast. So at a rate approximately 0.421 over n squared. So this is pretty special. Not because of the number on the top, I'm actually not sure what significance this has, but because of this denominator. So this specifically, okay, the power of the denominator, this in specific tells us something very special. It tells us the algebraic degree of the square root of 2. In fact, the algebraic degree of the square root of 2, you probably know if you've studied number theory, is 2. It's pretty simple because it's the solution to a polynomial with integer coefficients being equal to 0. It's the solution to a polynomial of degree 2 with integer coefficients. So, of course, the solutions to this equation are the square root of 2 and the negative square root of 2. You cannot find a polynomial of degree 1 with integer coefficients such that one of its roots is root 2. Now, quite expectedly, that implies that the irrationality or algebraic degree of any rational is 1. Because if I pick some random rational number like 1027 divided by 991, then I can very simply construct a polynomial of integer coefficients of degree 1 so that this is one of its roots. So I can just write 991x minus 1027. Set this equal to 0, and very clearly, one of the roots, in fact the only root, is 1027 divided by 991. You can do this with any rational number. So, what does this imply? In fact, if we try to construct a sequence similar to B over a B of n, where we try to get the closest rational approximations possible, it will follow a correlation similar to 1 over x. As you can see if you flip to, I'm pretty sure it's page 3. So you can notice a weird zigzag pattern, but more strikingly, you can notice that it actually declines a lot slower for this rational number that I randomly picked than for the square root of 2. So this is actually, and of course, this is not actually accurate. And the reason why is pretty simple. Now, 991 in specific is a prime number. I picked it that way. But there were some pretty close numbers, like 990, for example, that have lots of factors. I mean, 990 has 90 as a factor, which already means that it probably has tons of divisors. And so, at each of these divisors, if we try to find a fraction with denominator 90 that's as close as possible to this, we'll have a much easier time finding something that's very close to 1027 over 991, which is actually why, if you look closer at that graph, you'll notice occasional spikes, kind of like this. Because at each of these locations, we're approaching a divisor of 990. Even though that's not exactly the same thing as 991. And in fact, this is only 0 when we're exactly at 991. So this is the very fascinating thing about irrational numbers. For some reason, they seem to be approximated faster than rational numbers. And so, the goal today to show that a number is irrational is to show that the number, which I guess we can call alpha for now, minus some rational approximation to the number is always going to be less than some rational approximation that we can construct is always going to be less than the rate of decline for a rational number. So that's our goal today. This is what we're going to be seeking out. And the number we're specifically going to be doing it with is this guy, zeta of 2. Now, what does that mean? Well, the zeta function classically has a very simple definition. Technically, you can write this as a limit, but here it is. Now, there are all sorts of analytical extensions to this. So, normally, if you remember your calculus class, this should only be defined for s is greater than 1. Now, there are all sorts of analytical extensions that allow you to extend it to not just the entire real numbers, but the entire complex numbers, except for the number 1. The harmonic series is just screwed up in some way. So, however, we're going to ignore all these analytical extensions because in this field of mathematics, we're studying a very simple domain, the positive integers that are all greater than 1. And specifically today, we'll be studying 2, which is, the next simplest number. So, of course, if you try to write out zeta of 2, this is just going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. Now, with a number of methods that are pretty long and were first devised by Euler in the late 18th century, you can show that this is equal to pi squared over 6. I know, it looks pretty sketchy. And then, it was not shown until after Euler's death that pi was not only irrational, but also transcendental, which means that pi squared would have to be irrational as well. So, it took a pretty long time to show that it was irrational by directly calculating its value. But it had the bonus of showing that zeta of 4, zeta of 6, and in general, all even values of zeta were irrational. But today, we're going to do it by totally bypassing that, not calculating its value at all. Now, there's a pretty simple way to calculate its value. Should be somewhere out there on Wikipedia, if you're curious about the basal problem. But today, we're going to figure out that this is irrational completely differently. So we're going to start by attempting to write this as an integral. So, I'm going to split this up into 1 over n times 1 over n. Nothing seems very strange yet. And now, I'm hoping you'll agree with me if I say 1 over n is equal to 1 over n minus 0 over n. So that should be pretty simple. And now, I'm hoping you'll agree with me if I say that's equal to 1 to the n over n minus 0 to the n over n. Should be pretty simple to see why. And so, that's just equal to x to the n over n with bound 0 to 1. And that helps because this looks like a product of the inverse power rule. This is just the integral of x to the n plus 1 dx from 0 to 1. So, we can actually do that right here. So, I'm going to write this as, this is x to the n plus 1, so I'm going to write that as x1 to the n plus 1, and then I'm going to write this guy as x2 to the n plus 1, dx1, dx2. And of course, this is going to be from 0 to 1, and from 0 to 1. So you can think of it as an integral over the unit square, right over here. Now, just to keep things short, because I'm going to be writing this integral a lot of times, I'm going to call this unit square a. So hopefully you can just keep in your mind that this a means this Cartesian product. So this unit square right over here, from 0 to 1 on the x1 axis and from 0 to 1 on the x2 axis. So now here's what we can do. So you should know that the integral of a plus the integral of b is equal to the integral of a plus b. And so the same way, if we have an infinite sum, if we have the integral of a1 plus the integral of a2 plus etc. So if we have that infinite sum, that's going to be equal to the integral of the infinite sum of a1 plus a2 plus etc. Can I push this any further? No. So in this case, we can actually swap out this integral and this sum. So we can reverse their orders. So hopefully I can just move both of these to the side. Oh, this goes far. Okay. So I'm just going to rewrite this as the integral over that area A of the infinite sum. And I'm actually going to write these two together. So x1, x2 to the n plus 1, dx1, dx2. Now, the n plus 1 isn't very satisfying, and to put this in a form that probably looks a little more familiar, I'm going to substitute in m is equal to n minus 1. So what that gives us is, go over here, the integral over a of the sum from m equals 0 to infinity of x1, x2, m, dx1, dx2. And now it should be pretty apparent that this looks a lot like a geometric series. We have x1, x2 to the 0, plus x1, x2 to the 1, plus x1, x2 to the 2, and so on and so forth. Which makes it pretty clear that this is going to sum up to this. Now, you might notice, based off the integral limits being from 0 to 1, that this is going to vanish or diverge to infinity at the boundaries of this unit square. So just imagine we're taking an improper integral here. So this is equal to the integral over a of 1 divided by 1 minus x1, x2, dx1, dx2. Suddenly, we've written the weird infinite sum as a very simple integral. Technically not very simple, but it looks pretty nice. It's just an integral of a pretty simple continuous function over the unit square, which is a pretty simple domain. So now we're going to look at something a little bit different. I'm going to pull these guys back. We're going to look at approximations of zeta 2. Now, when we're approximating an infinite sum, the best way to do it is, of course, using a finite sum of the infinite sum. So, if we have this, then the best way to approximate it is writing some series, let's call it AK, that's equal to this. So, this is 1 over 1 squared plus 1 over 2 squared plus 1 over k squared. And so, your first instinct here when writing this is probably, sorry? Okay. Your first instinct when trying to rewrite this is probably to make it one fraction under a common denominator. So, the way we can do that is just saying that there has to be some integer, let's call it zk on top, and on the bottom, writing the least common denominator of 1 squared, 2 squared, 3 squared, and k squared. Now, here's something nice we can do. Now, I know this is probably going to sound dumb, but this is actually equal to the square of the least common denominator of these first few numbers. Why is that? Well, for this reason. When we're taking the least common denominator of the first k numbers, so let's say we're doing it with 10 for a short example. First, we have to search up which of the prime numbers are less than 10. And of course, they're 2, 3, 5, and 7. Now, we take 2. We search up what's the highest power of 2 that's less than 10. And that's 2 cubed, which is 8. Then you take 3, and you search up what's the highest power of 3 that's less than 10. And that's going to be 3 squared, which is 9. Then you take 5, and you search up what's the highest power of 5 that's less than 10. And that's 5 to the 1, which is 5. And the same thing happens with 7, which means that the least common denominator is just going to be the product of all of these prime factors. So that's going to be what? I think 2,520. So that's a pretty simple way to, bless you, find the least common denominator of the first consecutive numbers. But now, let's say we're doing it with 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared. Now, this looks terrifying because by the process that we've just used, we would have to search up all 25 of the primes that are below 100. But in fact, since none of these numbers, all of these numbers are divisible by very special things. 1 squared is only divisible by 1. 2 squared is divisible by 2, 2 squared, and all of its factors squared. 3 squared is divisible by 3 and all of its factors squared. 4 squared is divisible by 4 and all of its factors squared. And the same thing happens for the rest of them. None of these numbers are divisible by any prime higher than 7. So 11, for example, doesn't go into any of these numbers. Neither will 13 or 17. We only have to confine ourselves to the numbers that are still less than 10. And then we can search up what's the highest power of 2 that's present in this array. And of course, the only thing we have is going to be 8 squared, 64, 2 to the 6, 2 to the 3 squared. Same thing with 3. We're going to pick 9 squared, which is 81, 3 to the 4, 3 to the 2 squared. You probably see a pattern. Before, we picked 8, 9, 5, 7. Now, we're picking 8 squared, 9 squared, 5 squared, 7 squared. So it should be pretty clear that the least common denominator of all numbers 1 to 10 squared is equal to the square of the least common denominator of all the numbers from 1 to 10. And to be short, I'm going to abbreviate the least common denominator of the first n integers as dn. So in this case, it would be d10. So that means I can rewrite this as dk squared. So this is actually going to be very useful because of its specific properties that we'll explore a little bit later. But for now, we'll see that rational approximations to zeta of 2 have this very special form. So now I'm going to write an integral that should represent one of these rational approximations. Or rather, it'll represent the error to one of these rational approximations. An integral whose result looks something like this. And let me check what page that's on so you guys can follow. Okay, it should be on pages 6 through 7. Alright. So, if we try to write out one of these rational approximations, what is it going to look like? If we try to write out the error, zeta of 2 minus ak, that's just going to look like the sum of every number that's not covered by this guy. So it's going to be n is equal to k plus 1 to infinity. So, if we write that out, it should be pretty clear that this is equal to this. So, that's already a very nice simplification that we've made there. So now we're going to use the same trick that we did last time, where we turned this sum into this, and then we turned that into this, using this, and then we turn that into this. So essentially, we're doing that geometric series trick again. So I'm just going to speed through it this time, because hopefully you've already gotten the gist of how it works. So this is going to be 1 over k plus n, 1 over k plus n. We rewrite that as the double integral over that area of x to the k plus n plus 1, x2 to the k plus n plus 1, dx1, dx2. So that's the end of this whiteboard. So we can take it over here. So what's this going to be equal to? Well, we use the same substitution as before. Well, sorry, this would be minus. Oh, wait a second. Have I made that mistake? Oh my goodness. Did I write before that the integral of x to the n plus 1 dx is equal to x to the n over n? Because that is a mistake. This would be a minus. Sorry. So, if we let m is equal to n minus 1, just like before, then we can rewrite this as integral over the area of x1 k plus m, x2 k plus m. Alright, so we have this over here. We do the swap of the integral of the summation again, but this time we do a little something special, because we're not actually summing over k, we're only summing over m, which means that we can actually take out x1, x2 to the k, and keep the x1, x2 to the m. So this is going to be equal to x1, x2 to the k on the outside of the sum, multiplied by that geometric sum that we have earlier, which is just going to be 1 divided by 1 minus x1, x2, dx1, dx2. So this is a nice integral form, and as we've demonstrated before, this can be written as zeta of 2 minus zk divided by dk squared, where, of course, once again, dn is equal to the least common denominator of numbers 1 through n. Or least common multiple, you could say, but I'm going to say denominator. So, now we're going to do something even more bold. Let's try. Can we slide this one over? No. Okay. Looks like we're finally going to have to erase something. Okay. So let's try defining this number, which you'll see on page 8. Or, in other words, let's try defining this. So, surprisingly, this is actually equal to ZAB over DA squared. And let's see why. So, this is because we can execute the geometric series trick backwards. So I'm just going to speed through it without saying anything because we've done it twice. Hopefully you can catch on to how to do it a third time. So this is... And we replace this with that infinite sum. And now we essentially swap this back out. And once again, we have over a x1 to the m plus a, x2 to the m plus b. And now we fully reverse this by just rewriting it as 1 over m plus a plus 1 times 1 over m plus b plus 1. But if you remember, we substituted m is equal to n minus 1, which logically means n is equal to m plus 1, which means this has outlived its use, and we're going to switch this up for n plus a, n plus b. So now we're going to do something a little bit tricky. So without loss of generality, assume that a is greater than b. So then a can be rewritten as b plus some integer n. So let's rewrite it that way. Now we can use partial fraction decomposition, where we essentially assume 1 over n plus b plus n, and times n plus b is equal to a over n plus b plus n plus b over n plus b plus n, where a and b are some expressions. And so now, let's solve for a and b. Oh, did I really just do that? So, this gives us a times n plus b times n plus b plus n has to be equal to 1, which, let's try solving for it. This logically implies that a is equal to minus 1 over n, and b is equal to 1 over n. And of course, you can plug this into check. So you get minus n plus b over n plus n plus b plus n. Oh no, sorry. 1 over n plus b plus n. I switch the order of these to make sure. Okay, better safe than sorry. So you can check that this plus this is equal to this. So now, with that completed, we can rewrite this as, I'm going to keep this up in the corner, one over n plus b plus n, and we're going to keep the 1 over n on the outside. So we'll write this as 1 over n plus b minus 1 over n plus b plus n. So now, let's move this board over. This is the thing that wastes the most time. Alright. So now, what is this equal to? let's try writing it out. But first, let's substitute in a new variable for n plus b because it looks nice. So now we're summing over p. And what do we get here? We get 1 over 1 plus b minus 1 over 1 plus b plus n plus 1 over 2 plus b minus 1 over 2 plus b plus n. And I'm just going to continue the series. Plus dot 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 plus 1 over n minus 1 plus b minus 1 over n minus 1 plus b plus n, which is 2n minus 1 plus b, plus 1 over n plus b minus 1 over 2n plus b. And this is going to continue forever on that side. But what you'll notice is that, oh crap, should have written this, and then n plus b plus 1, and 2n plus b plus 1. And what you'll notice here, essentially, is that this will end up canceling out this. And the same thing is going to occur for this and some other term over, the same is going to occur for this and the next term over here. And that's going to go all the way, and this is going to get canceled out as well. So everything is going to reduce down to this. Let me make sure that's correct. Oh crap, wrong n. Because we're summing over n. Obviously can't be an actual variable. So this collapses down to the sum from b plus 1 to b plus n, which itself, we resubstitute in a is equal to b plus n to get that this is the sum from I equals 1 to a minus the sum from I equals 1 to b. And so, you might believe I've forgotten about this factor that we left outside a very long time ago, but in fact I have not. We're supposed to add that back into our product in order to get that this integral right here. How am I going to do this? Oh, this is an empty, oh, never mind. To get that this integral right here is equal to, let's erase this for a second, 1 over n, which we have a is equal to b plus n, which naturally means n is equal to a minus b, times the sum from I equals 1 to I equals a, minus this sum, which I'm just going to write as the sum from I equals b plus 1 to a. So now, here's what you're going to notice. If we multiply this, if we take this expression and multiply it by dA squared, what will happen? Well, we're assuming a is greater than b in this case. If I multiply this by dA squared, what is going to happen? Well, 1 over a minus b times dA squared times this sum So hopefully you'll realize that we can kind of divide and conquer. We can send out one of the DAs in order right over here to make this fraction into an integer. So this over here is going to be an integer now. And then we can send the other DA inside here. So, of course, this is going to be the sum dA over b plus 1 plus dA over b plus 2 plus dot 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 plus dA over a. And of course, dA is going to be the least common denominator or least common multiple of all of these numbers and even more that are less than b, which means dA divides into this, dA divides into that, dA divides into this. This is just a sum of integers, which means that this is an integer, and this is an integer, which means that somehow multiplying this by dA squared gives us an integer back, which naturally means that we can rewrite this as some random integer ZAB divided by dA squared. Alright, so now that we've defined this, we have one critical step remaining before the full proof, and that's going to be on page 9. So, the final step that we have remaining is limiting the value of this guy, dn. And so, that's going to work because of, I honestly can't find where I define dn anymore. But that is going to work specifically because of this process right over here. Because of that searching up process. So, essentially, if we're trying to find dn, we're searching up how many primes are less than n. And then we're searching up for each of these primes, less than or equal to. We're searching up for each of these primes, what's the highest integer power k such that p sub k is less than or equal to n. So, in other words, what's the highest k that's less than or equal to this? Or k is equal to the floor of this. Now we can use the prime, spoiled it. We can use the logarithm conversion formula in order to turn this guy into... Why is it so hard to split the pages of something freshly printed? We can split this guy into ln of n divided by ln of p, which is obviously less than or equal to ln of n over ln of p. So now, dn, that least common denominator, is going to be the product from, I have to think of an index. What index did I use here? Well, it's going to be the product of, for all the primes less than or equal to n, that prime number raised to this guy. Now, I'm going to make that less than or equal to this, of course. And I have to add the equal to sign because sometimes n is equal to integer power of the prime, which can make this an integer. That's just a side note. So, p ln of n over ln of p. Okay. So now, here's the final thing we have to figure out. P is just e to the ln of b. But that means that, where do I leave the red mark? Oh, it's in my hands. ln of p and ln of p cancel out over here, which means that we just get that this is equal to the product of all primes less than n of e to the ln n, which is just n. So that means we're raising n to some number, I don't know what to call it, x, where x is the number of primes less than or equal to n. But luckily, there's something we call the prime counting function that tells us exactly how many primes there are. And the prime counting function, by the prime number theorem, is approximately, I believe, n over ln of n. So this is approximately n to the n over ln of n. So sometimes this is a little bit too low, sometimes this is a little bit too high, but in general, it almost works. And so this is equal to e to the ln n to the n over ln n. So we cancel this out, and so that means that d sub n is less than or equal to, sometimes greater than, e to the n. So d sub n is approximately e to the n. And in fact, if you flip to, well, it's on page 10, you can see a nice graph of the dotted line is e to the x, and the dots are the least common multiple, or the least common denominator, or dn, of the first 50 integers. So you can see that this mostly holds true. Sometimes dn takes over e to the x a little bit, but as you can see, they're approximately the same. Also, if you're wondering why it looks so small, that's because we're using a logarithmic scale. Because, I mean, d50 is way bigger than d1. Same thing with e to the 50. So, that means that dn should concretely be less than 3 to the n. Okay, so now that we've done that, we can finally get to one of the most exciting parts. Now, first, I'm going to wave off some boring stuff pretty quickly. So, I'm going to write a very scary looking integral. So, I'm going to write, and this is on page 11, this guy. Now, this looks very evil. And actually, y is the substitution I used for x2. So I guess if you want this to look more familiar, I'll write this as 1 minus x2 pn x1 over 1 minus x1 x2 dx1 dx2. Now, I'm not going to go over the full thing because I want to show you something really cool, but in short, I'm going to say that if you use integration by parts, this is going to be equal to dn squared zeta of 2 minus one of these guys, za, that we defined a very long time ago, plus one of these guys, zbc, divided by dn squared. Now, to be brief, this guy's an integer, this guy's an integer. Why not just write it as an zeta of 2 plus bn divided by dn squared? I mean, this is the regular format that we always use for a rational approximation. So this is going to be what we use. And now, here's something pretty fun. Here's where the fun stuff starts. You might ask, what is this guy, Pn x1? Well, this is defined as, in this case specifically, the nth derivative of x minus x squared to the n, which in a more familiar form looks like x1 to the n times 1 minus x1 to the n. So, this looks scary, but in reality, we can do some pretty cool stuff with this. So, here's what I'm going to do. First, I'm going to write out p1 of x1. What is that? That's the first derivative of x1 minus x1 squared, which is pretty clearly 1 minus 2x1. Let me just put this over here. Oh my goodness. Okay. So, as you can see, this is pretty nice. So we plug that in for n is equal to 1 in specific, we have this. Now, I'm going to do a little bit of a maneuver. So what I'm going to do is I'm going to set this, I'm going to forget about these guys real quick. I'm going to take this and then put a derivative on the outside. So, I'm going to take an integral with respect to x1 specifically, and then take a derivative with respect to x1. And so now, what I'm going to be doing is using integration by parts. So, you can see the entire process of the integration by parts on page 11. So, you set u is equal to 1 over 1 minus xy. Okay, I'm just going to be reading off the paper during this part because I don't fully remember everything. dv is going to be 1 minus 2x1 So that means that this is just going to be equal to 1 minus x2 times d dx1 of x times 1 minus x1 divided by 1 minus x1 x2 from 0 to 1. And of course, if we're bounding it by x1, this is going to vanish as x1 approaches 0. This guy on the top is going to approach 0, and this guy on the bottom is going to approach 1, which means this is 0. We can ignore it. So, minus the integral of yx, or x2 x1, 1 minus x1, over 1 minus x1 x2 squared, dx1. So, that's all going to reduce down to minus 1 minus y times 1 minus x, xy, over 1 minus xy squared. So, this can be rewritten as minus 1 minus x, 1 minus y, xy, over 1 minus xy squared. Now, in general, I'm not going to prove it, but okay, you can see the intuition from here. This is going to be equal to am I reading everything right? This can be transformed into this. Crap. Caught myself using the old variables again. One minus x1 to the n, 1 minus x2 to the n, x1 to the n, x2 to the n, over 1 minus x1, x2 to the n plus 1. And you can see that specifically in here. So now we can do probably the most interesting part of this entire proof. So I'm going to erase everything else in preparation. So this is the most interesting part, the end of the entire proof. So what I'm going to do is actually show that 1 minus x1 times 1 minus x2 times x1, x2 over 1 minus x1, x2 over the unit square is less than or equal to, and get ready for this very dumb number, the golden ratio minus 1 to the 5th power. So this looks very out of place. So how can we actually show that this is true? So the entire proof of this fact is on the lower half of page 11 and the entirety of page 12. So here we go. This is going to be very fascinating. So let's try to find the minimum of this guy, and this is over the unit square, by the way. Of course, it gets higher when you get outside the unit square. So let's try to show that this is true. So first, we take the partial derivatives with respect to each variable and set them to 0 to find any possible minimums within our area. Now, if you noticed, this is symmetrical. We could swap the variable names around, and this would be totally identical. So, when I take the derivative with respect to x1, I'm just going to swap the variables and write it out for x2 instead, and hopefully you'll accept it. So, this is just going to be equal to what? This is going to be the partial derivative with respect to x1 of x1 minus x1 squared times x2 minus x2 squared divided by 1 minus x1 x2. So, do I not have it written down in terms of the old variables? Apparently, I do not. Okay. So, we're just going to write it down like this.
You might at the time,
Mhm.
We can take you for your word that it actually is the golden ratio minus 1 to the 5th power.
All right, got it.
And maybe we'll assign that to some of the students to be sure to check it for us.
Yeah, it's the entire proof is on page 12 if you're unsure, but just take me for my word, I guess. So it looks pretty strange though. So this is about 0.091, which is less than 0.1. So now that implies, what is this giant integral over here? Well, this is equal to minus 1 to the n. Well, this has to be less than or equal to minus 1 to the n multiplied by that thing to the 5n, because remember this entire expression is raised to the n, multiplied by the integral over a of 1 over 1 minus x1 x2. But if you remember from earlier, this is literally what we defined zeta of 2 to be. So that means that this guy over here, which is equal to an over dn squared zeta of 2 plus bn over dn squared, has to be less than or equal to minus 1 to the n, the golden ratio minus 1 to the 5n, zeta of 2. And now, to make this not look so tacky, we're going to say that this is less than, and actually, yeah, okay. So I'm going to put absolute value signs on everything, just because this guy will get in the way if we don't and mess up all of our inequalities. So if I put absolute value signs on everything, you suddenly have something that looks pretty nice. So this is 0.1 to the n, zeta of 2. And of course, this all has to be greater than 0. So I'm going to remove this guy because it looks weird. And now we have this. But remember from earlier that we said dn has to be less than 3 to the n when we were limiting it. Thus dn squared is less than 9 to the n, or 3 to the 2n. So you have, this is less than, or 9 to the n, plus bn over 9 to the n. Now we want to multiply both all of these guys, and we're going to pretend this guy doesn't exist. Now we're going to multiply everything here by 9 to the n. So we get 0 is less than an zeta of 2 plus bn is less than 0.9 to the n zeta of 2. And now we can see over here that somehow we've come to the conclusion that if we divide both sides by zeta of 2 at least, this means that the rate of approximation to 1 over zeta of 2 is this exponential function. And this exponential function will approach 0 much faster than any function of the form c over n. So that means that this converges, or rational approximations to this number converts faster than to any rational number. So that means that 1 over zeta of 2 is irrational. And as a byproduct of that, its reciprocal, zeta of 2, also has to be irrational, which completes the proof. So there are a few other very interesting problems in this area, some of which include dealing with the irrationality or the general forms of things like multi-valued zeta functions. So something like this, for example. So if you want a small exposition to other problems in this area, you can look at pages 13 and 14. So there have also been attempts made on zeta of 3, which worked a while ago, which uses a very similar apparatus, except that we wrote this instead as the integral over a of log x1, x2, x1, x2 over 1 minus x1, x2. But similar attempts have been made for zeta 5. It seems too complicated to write it as a unit square integral. So people have tried to bypass it by writing it as an infinite series instead, and showing that that converges much faster than any rational number would. But so far, we're grasping at straws because we have things like 1 over 294 pi to the 5 minus 72 over 35, the sum from n equals 1 to infinity of 1 over n to the 5 e to the 2 pi n minus 1 minus 2 over 35, the sum from n equals 1 to infinity of 1 over n to the 5 e to the 2 pi n plus 1. Needless to say, it's practically impossible to study the behavior of this as n approaches infinity. So, for now, it seems like we've come to a dead end until we figure out a new approach for attacking these problems. However, there are also things like multi-valued zeta functions, which actually have a very nice connection to linear algebra that you can find in Mazur's work, which should be somewhere in the manuscript on page 14. And in general, this is one of the most interesting and unexplored topics. This proof in itself is very complicated, but it's still very elegant. And most of it, by the way, is borrowed from Fritz Beukers, who proved this all the way back in, I think, the 1980s. So you should check out his paper for a much more concise, but also a little bit of a more advanced look at this topic. And thank you so much for attending this talk. And I hope that this proof and, in general, the discussion of this irrationality has been very enlightening.
So I'm glad that you've been a guest today, so that it reaffirms some of us are old-time folks, and we partial fractions, for example, we love them. Some of us still do. Some of us maybe don't like them as much. Or students certainly don't like them. So open up for questions.
I just watched a video on it one day, actually. I watched a video on proving that it was equal to pi squared over 6. And from there, I was very interested in number theory in general, and specifically how to show that a number was irrational. Now, since then, I've taken a few proof courses where we've been forced to show, for a few basic examples, that the square root of 2 is irrational. And eventually, I started wondering, how is pi shown to be irrational? How is e shown to be irrational? I kept exploring these proofs. I found it really interesting. So one day I tried to figure out how to prove that zeta of 2 is irrational without actually calculating its value, and then showing that was irrational.
But I appreciate that you started with the familiar proof of the square root of students that irrationality would be very intuitive. Mm-hmm. Here there were each step of what you did, except this thing integral, which after you said maybe you made mistakes because it looked like your powers were going the wrong way. But other than that, each step of what you said was I think, very clear. So I would guess that more proof of this is a better one for students that will have whatever we're listening for. But unfortunately, in real time, I wasn't able to follow all the pieces.
Yeah, I'm so sorry. I rehearsed this twice, and somehow I still made the power mistake.
It's just that people are at different speeds, right?
Yeah.
And what your interest in this particular topic of trying to prove that some of one of n squared is irrational.
What made me interested? I just watched a video on it one day, actually. I watched a video on proving that it was equal to pi squared over 6, and from there, I was very interested in, like, number theory in general, and specifically how to show that a number was irrational. Now, since then, I've taken a few proof courses where we've been forced to show for a few basic examples that the square root of 2 is irrational, and eventually, I started wondering, how is pi shown to be irrational? How is e shown to be irrational? I kept exploring these proofs. I found it really interesting. So one day I tried to figure out how to prove that zeta of 2 is irrational without like actually calculating its value and then showing that was irrational.
I just don't move at that speed in that. But it's like I think this is being recorded here, right?
Yeah.
So if I watch the video that Professor Thornton recorded, I think I'll have to be able to get.
Thank you.
So we have one more.
Is it your plan to study number theory when you get to NYU? You're entering in the fall, right?
Yeah, I already entered.
You're already there.
Yeah, I'm in my second semester. And I'm studying number theory, but I'm also looking for other research interests. I'm still in my first year, which means that I still have a lot of topics to go into, lots of things to study. And number theory is one of the things that has interested me at first. But also there were some more interesting and more advanced topics that I've looked into, like graph theory and ring theory, that I also think I might want to go into instead. But I think that this was one of the early higher level math topics that I found out about, which is why I was so.
I think let's thank the speaker again for a really.
Thank you.
And just to reiterate Professor Howard's observation, I mean, I think the strategy that we traditionally use is, to show directly that something like the square root of 2 is irrational. But then here, what in a sense we're doing is that we've somehow constructed some integrals, and we've shown that that zeta of 2 kind of, these integrals sort of converge in some sense. These integrals are rational, and that zeta of 2 are sort of converging to zeta of 2 in a really nice way.
Exactly.
And so you somehow there are questions there to ask, but we will save them for your next visit to Medgar Evers, and I suppose you'll be a professor someplace.
Yeah, so just to reiterate the main summary, all we did was, in the beginning, I gave you an intro to showing that rational numbers actually have rational approximations that converge really slowly, and all we did here was transform this into an integral, then transform a rational approximation to another integral, then we bounded the rational approximation and showed that it converged much faster than any rational number. And also, of course, to Professor Zudilin, who helped me throughout this entire process. And yeah, he couldn't attend because he lives in the Netherlands. But
No, that's fine. It was a long ride.
Yep.
So
thank you.
Let me just recognize one more professor from NYU.
Thank you.
And
Yeah, it's very complicated.
Yeah, it's unlikely to work. Yeah.
Yeah, I mean, as I detailed in the end, we've had two main approaches to this problem, and neither of them worked. Both of zeta 5 was impervious to both.
Yeah.
So we have to find a new method of attack for that problem.
Okay.
Yeah.
What will probably stay with me longer